multi-signature schemes, one session. So we have 2 more exciting talks before lunch. So the first talk is Chopsticks, fork-free 2-round multi-signatures from non-atypic assumptions, and that's by Jiaxin Pan and Benedikt Wagner, and Benedikt will give the talk.
Yeah, thank you. I think the audience does not see the slides. So.
All right, so we need the talk. We need the slides.
I will check in the region.
Okay, all right. Slides are coming up.
Okay.
All right, here we go. Yeah, Benedikt.
Cool. Yeah, thanks for the introduction. So this is this paper is called Chopsticks. Is about 2-round multi-signatures and how to avoid the forking lemma. And this is joint work with Jiaxin Pan. So yeah, let me first introduce multi-signatures. What are multi-signatures? In a multi-signature scheme, we have a group of signers, and they all have their independently generated public keys and secret keys. And now they come together to sign a message. And to do that, they may interact in some protocol, and after that, output a signature. Now, you can verify this signature using the list of their public keys. Okay, and intuitively, the signature should sort of certify that all of these parties participated in the signing process. So it should not be possible for you to output a signature without interacting with one of these parties. Okay, and this can be formalized by some notion of unforgeability, which is very similar to the standard notion for digital signatures, but I won't go into detail here. So why is this primitive useful? Well, one application comes from the cryptocurrency space, so this group of signers could be a group of users that share the ownership of some coins, and now they want to sign a transaction spending these coins. Okay, so that's the primitive. Now, I can give you a very simple and almost trivial construction of this. Just let every signer sign the message locally and then concatenate the signatures. So this is a construction. It is actually secure, but as the number of signers grows large, also our signatures become large. So with that trivial multi-signature in mind, it's really necessary to clarify the goals that we have when we construct these multi-signatures. And in terms of efficiency, I already mentioned this, the signature size is something we care about. This trivial multi-signature is not what we want. We want compact signatures. Of course, this is an interactive protocol, so we may also care about things like communication complexity, round complexity, or the computational complexity. Okay, and now in terms of functionality, there are 2 properties that I want to mention that sort of enhance the functionality that I described before. The first is called key aggregation, and this is a feature that you want to have typically. It says that you can not only have a compact signature, you can also have a compact form of representing your list of keys. So what does that mean? We take the list of public keys and we can aggregate them into a short aggregated public key, and then you just verify with respect to this public key. So this public key encodes sort of all these public keys and can be used for verification. Another additional functionality feature that we may want is pre-processing. Here, the entire interaction does not depend on the message, except maybe the last round. So you can pre-process the first few steps. And then, of course, we need some security requirements. And in terms of security, this is pretty much as for any other cryptographic primitive. We care about the assumptions that we use. We want minimal assumptions that are well studied. And we also care about the security loss if we treat the security reduction or the proof as a sort of a quantitative statement. Okay, with these goals in mind, let's look at the state of the art. What do we already have? And here I should clarify, I only look at schemes in the discrete logarithm setting. I don't allow pairings here, and especially I don't look at other assumptions like lattice-based constructions or something like that. We have a very prominent 3-round scheme by Belara and Nevin. They introduced a scheme which is basically a variant of Schnorr signatures turned to the multi-signature setting. And as for Schnorr, this is proven under the D-log assumption. And as for Schnorr, they use rewinding, which leads to this kind of security bound. So here, epsilon is the advantage of the adversary, and epsilon prime is the advantage of the reduction against the D-log assumption. Then, in the same paper, they give a construction which is tightly secure based on DDH. And you can sort of tweak these two constructions a bit and get the music scheme and its tight variant. The advantage of this scheme is that it allows for key aggregation. So this key aggregation feature that I described before, these schemes have it. The price that they pay is now they need to apply rewinding and the forking lemma twice. So they take the adversary, rewind it, and then take the result and rewind it again. This leads to this security bound with epsilon to the power of 4. Okay, now looking at 2-round schemes, there's a very prominent scheme called Music 2, which also has this nested rewinding strategy, and it even comes from a stronger assumption, the one more discrete logarithm assumption. And then there's a scheme that is HBMS, and it's basically as for Music 2, just the assumption is weaker. You have the D-log assumption here. Okay, so if we look at this situation, then what we see is that especially the security bounds for the 2-round schemes are completely useless if we treat this as a quantitative statement. So let's say you have a standardized curve and you use that to implement your scheme, then these bounds don't give you any meaningful security guarantee. And this comes from the rewinding or even this nested rewinding strategy. So our question was, is this rewinding inherent in the 2-round schemes, or can we have a scheme that does not use this rewinding strategy? Okay, so concretely what we wanted is we wanted a scheme that is 2 rounds. It should come from non-interactive assumption. I don't want to make the assumption that the scheme is secure or something like that. And ideally, I avoid this rewinding, and even better, I get a tightly secure scheme. So that was our goal, and we actually achieved this. So with our two schemes that we propose, we have 2 schemes based on the DDH assumption. Both of them have 2 rounds. And the difference is that one scheme is not fully tight. It has a security loss proportional to the number of signing queries that you have in the security game, but it allows to aggregate your keys. And the other scheme is fully tight. Okay, so for the rest of the talk, I want to talk a bit about the technical details, but I don't want to go too much into detail, especially because I don't have enough time for that. If you're interested in the technical details, come talk to me. I'm happy to talk about it or look into the paper. Okay, so we want to construct multi-signatures, and a good start is to look at what has been done for standard signatures. So how can we construct standard signatures? And one way to do that is to start with an identification scheme. For example, the Schnorr identification scheme. So here you don't have to understand all the details if you're not familiar with it. Just let me recall the high-level structure. First, there's a prover that sends a nonce R. It gets back a challenge C from the verifier, and then it has to output some response S. Again, the details are not important, but what you may notice if you are familiar with Schnorr signatures and Schnorr identification is that I replaced certain parts with this linear function f here. So this will come in handy later. And now what Belara and Nevin showed is you can turn this into a multi-signature scheme. And the rough idea is that every signer sort of locally runs this Schnorr identification protocol, but after each step you take these messages, for example the nonces, and you aggregate them. And because this is all nice and linear, this sort of works out. Okay, but what we also see here is that there's an initial round where each party sends the hash of their nonces. And this is very important. It makes sure that the nonces are sort of independent, and if you don't have this round, there's actually an attack against the scheme. So that's the Belara and Nevin scheme, and the same structure is also what happens in the music scheme. Okay, so again, this is the scheme. I just write it now from the perspective of one signer. What are the messages that one signer sends? And if we look at the drawbacks, then this is a 3-round scheme. We want a 2-round scheme, so that's one thing we have to improve. And the second problem is that it uses rewinding, right? So it's based on Schnorr, and for Schnorr, if you want to take the forgery and use it to solve the D-log problem, you need a rewinding step, and the same holds true for these multi-signatures. Okay, so these are the two problems, and actually they have been studied, and people try to remove that. One way to remove the rewinding is to use this technique called lossy identification. This is a technique used in the literature on tightly secure signatures, and the idea is that you replace the instantiation of this function f with a non-bijective function. So that's all you change, everything, the rest stays the same. And you can actually show now that you get rid of the rewinding, but of course we didn't change much. We still have 3 rounds. Okay, so now let's think about the 3 rounds, and in particular this first round where everyone commits to the nonce. This is sort of what's annoying us. And here there's a very cool work from Darmgard and others, which uses homomorphic trapdoor commitments to get rid of this first round. And the idea is that I want to make the nonces independent of each other, so I should hide them. That's why I use a commitment. And to make sure that I can still aggregate them, I need a homomorphic commitment. And then in the security proof, I need an equivocation trapdoor. Okay, so they get a 2-round scheme in the lattice setting, actually. But now the problem of this is it uses rewinding. Okay, so an obvious question that you could have is, can you combine these two ideas? For example, can we take the scheme by Darmgard and others and just instantiate it with this new linear function that gives us tight security? But the problem is that this does not work. And this has also been noticed in Darmgard et al.'s work. So the problem is really that you have this trapdoor commitment, and this can only be computationally binding. So at some point you will reduce to the binding notion of this trapdoor commitment, and the only way you can sort of produce a collision there to break binding is to use rewinding, even if you instantiate it with this new function. Okay? So that brings me to the main challenges we had to solve in this work. The first one is what I just explained. So how can you combine these two techniques in a way that gives us what we want, a 2-round scheme that does not use rewinding? And the second challenge, and this is a bit subtle, so how do we construct this commitment? Actually, what I showed you, this Darmgard and others paper, this is based in the lattice setting, right? And we don't have such a commitment in the discrete logarithm setting. And if you think about the properties that we want here for a while, especially that we want to commit to group elements, but then we want to equivocate and open the commitment to an arbitrary group element, well, the opening will be something like an exponent. So this corresponds to, intuitively at least, a D-log trapdoor, and we don't have something like that. So that's the two challenges we had to solve, and I don't want to go too much into detail about how we solve them, but let me give you 2 ideas that we use. The first is, well, for the first challenge, the problem was that the commitment was computationally binding. If I have a statistically binding commitment, everything works out, but then I don't have an equivocation trapdoor. And so the idea that we had is we require a dual mode commitment, and if you combine this with other tricks, you can actually make it work. And depending on how you combine it with other tricks, you get either a tightly secure scheme or at least a scheme without rewinding. Okay, but this, of course, has an impact on our second challenge. Now this gets even harder. Right? Okay, and here the idea is that we have to solve this problem, so we don't come up with a D-log trapdoor. Instead, we say, okay, if we look at the reduction, then we only have to open the commitments to messages of a certain structure. So instead, what we require is not a full equivocation trapdoor. We require a trapdoor that is weak in a sense that it allows us to open commitments to messages of a certain structure. This is all I want to say about this. Okay, so let me summarize what we have seen. And so we have these 2 multi-signature schemes. Both are 2-round schemes based on the DDH assumption. The first scheme has this linear security loss, but at least it does not use rewinding, and it has key aggregation. The second scheme has a tightly secure proof, or has a tight proof. Okay, so I want to finish with some open problems, and if you have any ideas, I'm happy to talk about this. So the first obvious question is, can you get the best out of the two worlds, right? So I want to have a scheme that is tightly secure and it has key aggregation at the same time. And it's not clear to me how to do that, but I think this is an interesting problem. The second open problem, I mentioned this pre-processing in the beginning, where all but the last message of the protocol is independent of the message that you want to sign. And actually in our protocols, you already need the message in the first step. So our protocols don't have this feature. Would be cool if you can have it and still have all the advantages of our protocols. And the third problem, and I think this is the most natural one, so we have all of this based on DDH in a sort of a discrete logarithm setting. Can you have this from other assumptions? And I think what is very promising is from lattice assumptions, because there we already have some kind of commitment that satisfies roughly what we want. Okay, and with that, I finish a bit early, but yeah, thank you.
Thanks, Benedict. Plenty of time for questions. Please come to the microphone. Can you come to the microphone, please? Yeah. Otherwise, nobody can hear you. Sorry.
Okay. So if you compare apples to apples, like, you just pretend that these exact security claims are, so I guess if you don't compare apples to apples, right? So you can have a view that these exact security claims are not so important, that maybe it is still secure in spite of the fact that there is a security loss in the reduction. So in that case, how much, I suspect that your signature is longer. Mm-hmm. How much longer?
So the non-tightly secure one is, I think, twice as long as music, roughly, in terms of number of group elements that you have in the signature. And for the tightly secure one, it's an additional factor of 2, so that would be something like 4 times the size of music in terms of group elements. That's what I have in my head.
And the public keys are same or also larger?
The public keys for the non-tight scheme is the same. For the tight scheme, it's you have basically 2 components, 2 public keys, and yeah. So you have. Oh wait, so actually it's. so you have this additional factor of 2 that comes in when you go from this function, this bijective function, to the non-bijective function. So I guess everything that I just said, except for the public keys, multiplied by 2.
Oh, okay.
So to summarize, the non-tight would be 2 times the size of a standard D-lock key, and the tightly secure scheme would be 4 times.
Okay, sorry. And if you have interactive assumptions, does it become much simpler or not?
I think the interactive assumptions would help you to simulate the signer during the security proof. What they don't help you is getting rid of the rewinding, right? So I think maybe with less effort you can get a scheme, but it's not obvious to me how to. Yeah, I hope this answers your question.
Yeah, thanks for the nice result. So you mentioned the weak trapdoor property. So I'm quite interested in this. So like, don't you need a user equivocal commitment? Like you need some weaker property?
What do you need? Didn't get the
sorry, so I was wondering if you only need any property that's weaker than the user equivocal commitment scheme. Yeah.
Okay, so what I need is that I give you a commitment, and then later you give me sort of a message of a certain structure, and if the message has this certain structure, then I can open the commitment to it.
Okay.
Okay. So and for those familiar with like Schnorr and things like that, the structure corresponds to the output of the honest verifier zero knowledge simulator. So I know that all my messages that I want to open the commitment to have this structure, so I can prepare the commitment in a special
I
way.
see. So you don't need to equivocate to any message. Like you
No,
don't-
just any message that follows this structure.
I see. Okay. Thanks.
Okay, yeah, let's thank Benedict again. All right, so the next talk and the last one of this session is on threshold and multi-signature schemes from linear hash functions by Stefano Tesaro and by Zhenxi Xu. And Zhenxi will give the talk.
Hello, everyone. So today I'm going to present of a paper, threshold multi-signature schemes from linear hash functions. It's a joint work with my advisor, Stefano Tesaro. So before we start, I would like to clarify that this talk is about pairing-free threshold and multi-signatures. So comparing the pairing-based scheme with pairing-free schemes, the latter have a broader library support and it enables efficient signature verification and requires weaker assumptions such as D-log and RSA. So now I'm going to introduce the notion of multi-signatures and also threshold signatures. So in the setting of multi-signatures, the user want to sign a message. Okay, I don't. Just realize there's no animation. Okay, okay.
Can we switch to a PDF version, maybe?
Okay, maybe. Okay, okay, that's fine. Okay, yeah. So yeah, sorry for that. In the setting of multi-signatures, the user want to sign a message. On a message to be signed by multiple signers, where each signer has its own public and secret key pairs. So the user will send a message to one of the signers, and then all the signers interact with each other before sending the signature back. And the signature can be verified given all the public keys, and we require the signatures to be much smaller or independent of the size of the numbers of the signers. And then the security requirement is that the signatures is valid if and only if all the signers are involved. And in the practical use of multi-signatures, we also require there's an ideal feature that's called the key aggregation, where so this feature allows us to aggregate all the public keys into a much shorter one, which can be used for verification. And in the setting of threshold signatures, so it's slightly different, where the public key and all the secret keys are generated by a distributed key generation protocol. And once the user sends a message to one of the signers, a subset of signers with size at least T was involved in the signing and send the message back to the user. And then the signature can be verified given the public key. The security guarantees that the signature is valid if and only if at least T signers are involved. And the use of multi-threshold signatures is so the motivation of using that is to avoid single point failure. And research in this area has become increasingly active due to its potential to enhance securities in the crypto wallets. And also the recent standardization efforts by NIST and IETF also highlights their importance. So what is this work about? So when investigating the existing group-based constructions of multi-signature threshold signatures, we find that the security of the most efficient schemes all require this algebraic one-more D-log assumption, which is suspected to be stronger than the plain D-log. So in this work, we're trying to remove these assumptions. So in this work, we demonstrate that there's a way that we can convert these group-based schemes into ones that based on linear hash function. And moreover, we show that the security is implied by the algebraic one more pre-image distance of the linear hash function. So this algebraic one more PR is a new notion we proposed. And then finally, we show that such a linear hash function can be instantiated from the either the plain D-log or the RSA assumption. So as a result, we give the new construction for this multi-signatures and threshold signatures that possess the same property as the original scheme, but based only on D-log and RSA, which solve several open problems in the area. And we'll next give a detailed comparison between our work and the prior research. So let's start with the multi-signatures. So before that, so note that the security of all the scheme we present here include our own. They're all proved in the random oracle model. So here, the offline rounds refers to the rounds that is independent of the message, and the online round refers to the message dependent round. So currently, the best we can do here is one offline round plus one online round, which is also refers to as partially non-interactive. However, in order to achieve this, we require either the algebraic one-more D-log assumptions or assuming that the algebraic group model, which we want to avoid. In the prior works that requires weaker assumptions need at least 2 online rounds, which includes also the chopstick scheme that presented in the prior talk. But it should be noted that the advantages of chopstick that it has a tight security reduction. And it's also worth mentioning that there are RSA-based multi-signatures, but they either require a trusted third party to generate keys, or they only support sequential signing, which is undesirable for practical use. For the threshold signatures, the only existing non-interactive, provably secure, and group-based schemes is Frost, which needs the algebraic one-more D-log assumption. And the other scheme proposed by Shoup is a RSA-based scheme. Their signing protocol consists of only an online round, but their security relies on the DDH assumption in some integer group, which is a non-standard assumption. So it's we're also important to note that here we consider a strong security goal, where the adversary is considered it's hard to forge a signature unless at least T minus the number of corruption of only signers sign. So for the weaker security, Schnorr's, for example, the Shoup's basic schemes requires only RSA, but their security only guarantees that it's hard to forge a signature unless one only spot is signed. Furthermore, all other RSA-based threshold signatures do not consider this stronger security goal, although they consider other properties such as the proactivity, robustness, removing trusted dealers, or the adaptive security, which are not focus of this work. So in short, to propose the first partially non-interactive threshold and multi-signatures based only on the login random oracle. And we also propose the first non-interactive threshold multi-signatures with the desired properties based only on RSA in the random oracle. So for the rest of the talk, I will first record the notion of linear hash function and show how our convergence work. And then I will focus on how to instantiate this algebraic one more pre-image resistant property from either D-log or RSA assumption. So a linear hash function is a function that from the domain D to a range R, where D and R are vector space with respect to a scalar S. And here we require the F to be subjective, and also compressing, which means the domain size is larger than the range. And in addition, we require the F to be linear, and also collision resistance. So intuitively, a linear hash function is a collision resistant hash function with linear structure. And now I will show our idea of how to do the conversion. So it's fairly simple. So given a group with generator little g and a size p, the idea is to convert all the exponential operation, this g to the x, with the f of x. So correspondingly, we also replace the zp with domain d, and the g with r, and also all the group operations with the operation in r. And then the d-log of y to the base g is corresponding to the pre-image of y on the f. So let's take the Frost scheme as an example. So here's the signing protocol Frost, and then here's the schemes after our conversion. So here I would not go into further details. I just want to give you an idea of how our convergence looks like. So I also like to briefly highlight the signature we produced by this linear hash function based Frost. So in particular, for the d-log instantiation from of the linear hash function we used, the resulting signature is as follows, which is exactly the Okamoto-Schnorr signature. So to show the security of the linear hash function based Frost, the idea is to apply the same conversion to both the assumption and the reduction. So the original proofs shows that the security of the Frost is implied by the algebraic one-mode d-log assumptions. And by applying the convergence, we can convert the algebraic one-mode d-log assumptions to the algebraic one-mode pre-image distance of the linear hash function. And then we can show that security of the linear hash function base Frost is implied by the algebraic PR property by adapting the original proof. So here I will not delve into how we adapt the proof because of the time limit, but I will briefly explain how we derive the notion of this algebraic one-mode PR property. So let's start by reviewing the one-mode d-log assumption. So it's defined using the following game. So the challenger first samples n-group elements, random group elements, and as challenges and send it to the adversary. An adversary has access to a d-log oracle, which takes an input, group elements, and returns its discrete log to the base G. And so the goal of the adversary is to output, so it's to compute all the discrete log of the challenges. So discrete log of all the challenges. And the adversary wins if all the discrete log challenges are computed correctly, and the number of discrete log queries is less than n. So the algebraic one-mode d-log assumption is a weaker assumption, where the crucial difference is that the adversary, in addition, need to provide an representation alpha of y with respect to all the challenges. Notably, so given the y, given the alpha, this d-log oracle is efficiently implementable, since the challengers can compute this y as the sum of the alpha I times xi, and which also means this assumption is falsifiable. And then by applying our convergence, we can adapting the one-mode d-log assumption to the linear hash function settings. So here the main difference is that we replace the d-log oracle with this pre-image oracle, which takes an element in R as input and returns an element in the pre-image of Y on the F. And here, the adversary, in order to access to the pre-image oracle, it must provide the representation alpha, and thus the challenger can compute this little y as the sum of alpha times the xi. And the goal of the adversary here is to find a pre-image, so find an element in the pre-image of each challenges such that, using less than n PI queries. So therefore we call this game the algebraic one-mode pre-image resistant game. So for the rest of the talk, the main challenges to show how we can construct this linear hash function such that its algebraic one more PR property is implied by either the D-log or the RSA assumption. So we're achieving that through a two-step process. So the first step is we show that the algebraic one more PR property is implied by the collision resistance of the linear hash function. And then so the second step is to construct this linear hash function such that the collision resistance property is implied by the D-log and the RSA. And so here our main contribution is in the first step, where for the second step, we just adapted the previous constructions, like for example this D-log instantiation, which we mentioned before. So for the rest of the talk, I will focus on to show how to show the collision resistance implies the algebraic one more pre-image resistance property. So formally, we have the following theorem. So for any algebraic one more PR adversary A, there exists an adversary that breaks the collision resistance property, such that the advantage of A is not greater than twice the advantage of B. So the construction of B is straightforward. So the idea is we just let B run A faithfully by simulating the algebraic one more PR game. So more precisely, the B initially samples n challenges and send it to the adversary A, and then for each PI queries, it answers it following exactly the same as the one more PR game. So after A returns, if A wins and the output of the A is not exactly the same as the one that generated by B, then B can find a collision. And this is because both the xi and xi hat is now in the preimage of f big X. So invert the preimage of big Xi and f. So then we just need to show that this deviation occurs with high probability. So here the key observation is that the execution of y is completely determined by the little x sampled initially. So for the x that makes A wins, so to show that this x is different from the output, the idea is to construct a mapping phi such that it maps the x to a different x prime, such that the view of A given x is identical to the view of A given x prime. And therefore, we can see the output of A should be identical in both cases. And therefore, we have either the x is equal to, it's not equal to x hat, or the x prime is not equal to x hat. So here's the type. And then we'll see that the B wins in one of the two cases. So then the proof goes through if the phi is a bijection. And then it's left to see how to construct such a phi. So we construct the phi, so we define phi x as x plus B times D0, as a D star, where D star is a non-zero element in D, such that it maps to 0 by F. We know such a D star must exist since F is a magnitude 1 function. And also, as B is a non-zero vector in S, such that the inner product of B with any representation sent by the A is equal to 0. So here we know the B must exist since the number of PR queries is less than n. And now to see why the view of A given x is identical to the view of A given phi x, we just need to show that the A received the same challenges and also the same answer for all the queries. So for the first, we just prove that, so the F given phi x is equal to Fx. So here the reason that this equation holds is because this Fz star is equal to 0. And for the second, we see that A received the same answer because this inner product of alpha times B is equal to 0. And we can also see that we can also show that this phi is a bijection, but I will not delve into it. It's the time limits. So to conclude, I would like to mention a few future directions. So first is to investigate the possibility to extend our result to the post-quantum setting. with the aim of constructing better post-quantum secured multi-signature or threshold signature. Another is to identify other areas which we can apply our techniques to remove the algebraic one multi-log assumption. Yeah, so here's all of my talk. Yeah, thank you.
All right, thank you. Time for 1 or 2 questions. I have one, if I may. So, so the post-quantum is still an open problem, no? But there is a linear hash function from lattices, no? It's essentially the cis or ISIS problem. And there's this one more ISIS problem. Did you try to use this one more ISIS problem to build a lattice-based, whatever?
Yeah, that's a very good.
And if so, is there anything? What were the difficulties?
Yeah, actually, that's a definitely very good attempt. But we also try it, but there's suspect to have a problem with the field, and because there's I think for the multi-signature schemes, they already post-quantum secure one that is very similar to you apply this one more SIS to the to our framework. So then the question is whether we can get the construction from the threshold settings. But for that, there's some problems with this one more SIS, which is not very compatible with our framework. Because for them, they can get this linear hash function, but with actual filters, which, so have to consider it differently.
Okay. All right. Let's thank the speaker again. And it's lunchtime.